This demonstration is measurement of hydraulic conductivity in granular material using the constant head method, ASTM D2434. The configuration is shown here, the test configuration that we're going to use consists of a few parts. First part is the reservoir that we're going to maintain filled with water at a constant level to maintain a constant head. We have a permeameter here full of some granular material, some sand. We're going to flow water through this sand and measure the flow rate. We have some graduated vessel here for measuring and quantifying that flow volume. We have a manometer, which is hooked up at two ports within the permeameter, so we can measure the head at two different points within the specimen. And we also have a timing device for converting flow volumes into flow rates. Let's take a closer look at each of these different components. Here's our permeameter. Our permeameter basically consists of some granular soil, either sand or gravel, inside an acrylic tube, sandwiched between a top and a bottom plate, held together with 3 rods. There's a core stone beneath and above the granular material, and a spring between the top plate and the core stone to provide some confinement to the soil. We're going to be bringing water into the specimen through an influent port, which is in the bottom. The water will flow up from the bottom and out through an effluent port here, and we'll measure that flow volume. We have 2 ports along the side with some spacing, L sub C. That's the vertical spacing between these ports. These ports are hooked up to a manometer. That's what these tubes go to. Let's take a little bit of a closer look at the manometer. So here's the manometer. These are my tubes coming out of the ports. And as we permeate water through this specimen, the water level will rise some given height in each of these tubes. We're going to measure the head loss across these 2 ports. And that head loss will be basically the difference in height of the water level between the 2 tubes. That head loss we'll define as delta H. Here I've also added some large graduated vessel. We're going to want to measure and quantify the flow volume, and we have some timing device, and we're going to measure the time. So we're going to come up with a flow rate, lowercase q, which is flow volume per unit time. So now let's take a look at the constant head reservoir and see how that works. The constant head reservoir consists of some water source. This line here is just connected to tap water. Some line that's going to be connected to the permeameter. This is the influent line of the permeameter. And then we want to keep it at a constant head. We don't want it to overflow, so we have some overflow port, and this line just goes to a waste bucket. So now let's take a look at the whole system again. So in review, here's the whole system. Permeameter, manometer, timing device, some graduated vessel for measuring flow volume, and some constant head reservoir. We're going to calculate hydraulic conductivity using Darcy's law. And in order for Darcy's law to be valid, the specimen has to be saturated. So the first thing that we need to do is saturate the specimen. Here's how we do it. We're going to take the effluent line and we're going to hook that up to a vacuum. I'm going to close the influent valve. I'm going to close the 2 manometer valves. I'm going to open this effluent valve, and I'm going to apply vacuum for 15 minutes. 15 minutes after I'm going to start permeating water through the specimen. I put some water in my reservoir. Now I'm going to open the influent valve and I'm going to allow that water to start coming through the specimen. It saturates very quickly. I close the valves. And now I'm ready to begin my test. Ready to start testing, but before I begin the test, I want to make a few measurements. I need to measure the vertical spacing between the manometer ports. That's L sub C. And I also need to measure the cross-sectional area of the specimen through which the water is going to permeate. The diameter would be D and the corresponding area would be A. So now, I'm going to open up the valves, and I'm going to measure some flow volume over a period of time. The flow volume is uppercase Q. And the period of time over which that flow volume occurs is lowercase t, which I'll measure with some timing device. So here we go. I open the valves, open my manometer port valves. I see my water falling, so I'll adjust my tap to try to keep up with that. And I'll permeate for 5 minutes or so. This is a 3,500 milliliter beaker, and so I'll permeate until I'm about half full or full with this beaker, and I'll record the corresponding time that it takes for that to occur. So I'm coming up to 3 liters. When I hit 3 liters, 3,000 milliliters, I'll stop my clock, and I'll record the time corresponding to 3 liters. Remember that 1 milliliter equals 1 cubic centimeter, so that's very convenient, and that will help facilitate calculating hydraulic conductivity. So that's half the measurement. The other half of the measurement involves deriving the hydraulic gradient, the loss in head, over some flow length L. Here, our flow length is L sub C, and our loss in head can be derived by just looking at the difference in the water level between these two manometer tubes. The difference in the water level is delta H. Given delta H and L sub C, we can calculate the hydraulic gradient. And given the flow rate and the hydraulic gradient, we can calculate the hydraulic conductivity. That's it for now. The next demonstration will be measurement of hydraulic conductivity in granular material using the falling head method. Thanks. See you then.